In this video, we'll look at model-based ways of estimating animal abundance, and we'll see how these are different from the design-based ways we've been looking at in the last two. The key thing about model-based inference is that we rely on building a model rather than a randomized design to get our estimates. We'll return to this example that we've been using in the last two videos. Just to recap briefly, we've got 51 plots arranged horizontally next to each other, and each of those plots has got a certain number of animals in it. We don't know what these numbers are, but what we'd like to estimate is the total number of animals across all 51 plots. To do this, we'll draw a sample of 6 plots. In design-based inference, our estimate is based on a simple random sample of 6 sites. This means that if we redo the survey, we'll land up with 6 different sites and therefore a different estimate. Uncertainty in the estimates comes from the randomness in the design. In contrast, with model-based inference, we try to build a model that will predict animal abundance from some covariate. Here, that would need two things. Firstly, we'd need to know that animal abundance is partly dependent on horizontal distance, and secondly, we'd have to have a way of measuring that covariate. Assuming that we've got those at each of our 6 sites, we can fit the regression line shown by the red line. That model allows us to predict animal abundance at any of the 51 sites. The small numbers in red are model predictions for the number of animals at each site, based on the horizontal distance in our model. We can add these up over all 51 sites to arrive at a final estimate. Based on these sites in our model, we come to an estimate of 2,414, very close to the true value of 2,429. Remember, with design-based inference, uncertainty in the estimates comes from the randomness in the designs. In contrast, in model-based inference, uncertainty in the estimates comes from uncertainty in the model itself. Here we've plotted the confidence intervals around the regression line. It's this uncertainty that gives rise to uncertainty in our final model-based estimates. If you've fitted a linear model before, you'll be familiar with the table of beta coefficients and associated standard errors. It's these standard errors that are driving the uncertainty in our model-based estimates. Using model-based inference doesn't mean that survey design isn't important. If we choose our sites badly, we can land up with a poorly fitting model that extrapolates way beyond the range of the data used to create the model. The key difference is that with model-based inference, the goal isn't to choose a random design, but to choose a design that spans the covariate space well, such as this one. This allows us to get a good idea of the covariate relationship and to avoid extrapolating beyond the range of the data. To summarize, in model-based inference, it's the model that does the bulk of the work. Calculations of variances and confidence intervals come from a fitted model, and this model allows you to predict throughout the survey area. A model doesn't use inclusion probabilities, so it doesn't need a probability sample, but it can use one if it's available. That means that you can build model-based estimates based on a randomized design. The opposite isn't true though. If you've built your survey for model-based inference and you don't have inclusion probabilities, you can't do design-based inference. With model-based inference, the main goal is to estimate the relationship between the covariate and the outcome of interest well, and your best chance of doing this is by sampling the covariate space well. That means including both high and low values of the covariate. We've now looked at 3 videos introducing the basic differences between design-based and model-based inference. Just to summarize these, with design-based inference, it's the design that does most of the work. We need to have inclusion probabilities and a probability sample based on those inclusion probabilities. That will involve some kind of randomization. We also need a big enough sample size to estimate whatever we're interested in reliably. Stratification is a way of dividing up the survey area into smaller subregions, and it's a useful way of reducing variance and getting more precise estimates. With model-based inference, it's the model that does the bulk of the work. What we're aiming to do is to estimate the relationship between covariates and the outcome of interest well. This means that we need a big enough sample size to estimate that relationship well, and we need a range of covariate values so that we're not extrapolating too far beyond the range of the data.